Assalamualaikum and very good day. I'm Dr. Hidayah from the School of Civil Engineering, Faculty of Engineering, University Technology Malaysia. First, I would like to welcome everyone to my lecture video. This video is for online learning for the course of Highway Engineering. In this video, I will continue my discussion on road construction focuses on field density tests. Okay, in this lecture, we will discuss on the soil compaction, particularly for the layers of the subgrade, subbase, and road base, or to be exact, is for the unbound granular materials. Basically, soil compaction on site depends on few factors, including soil characteristic, moisture content, machineries, and layer thickness. Prior to the field compaction, the laboratory compaction test should be conducted to determine the maximum dry density and optimum moisture content of the soil to be used on site. This is very important as later the maximum dry density value will be used as a guide for comparison to determine the achievement and acceptability of the compaction level on site. The field compaction is determined by number of passes, layer thickness, and tri-lay at the optimum moisture content. Okay, let's have a look on this link. Okay, this photo shows the field compaction of the subgrade using single steel wheel roller. So, how to ensure the field compaction undertaken by the contractor achieve the specification? And what is the quantity checking on site that can be conducted to verify the compaction works? Currently, there are various methods available for the verification of field density, whether it's non-destructive methods or destructive methods. The most conducted methods are sand replacement or sand cone methods, which is the most applied method in Malaysia. Other methods of FDT or field density test are core cutter, which is normally used for cohesive soil, nuclear or non-nuclear density gauge, which is almost can be considered as non-destructive method, and rubber balloon method. So using this method, the soil field density or degree of compaction, DOC, will be measured and compared to the target roadworks specification as recommended by the Public Works Department. So basically, the value of dry density measured on site will be compared to the maximum dry density value measured in lab through the compaction test. This plot shows the relationship between dry density and moisture content in lab. The DOC value is calculated in percentage, and the specification is based on the materials compacted, which is also depends on the road layers. According to Public Works Department specification, detail of the compaction level targeted for each of the road layers are shown in this figure. For the granular materials, which are specified for the use in subgrade, subbase, and road base, which is highlighted in blue. For subgrade, the target compaction of soil is more than 95% for the cohesive material and 100% for non-cohesive material from the maximum dry density. For subbase, the target compaction level is more than 95%. And for the road base layer, the target level is also more than 95%. For the bound layers made of asphalt, the compaction level will not be discussed further in this video, but detailed evaluation of the asphalt layers will be found in the next video. Okay, now we look into details of the methods used to determine the field density for granular materials, whether the specified compaction is achieved or not. It should be noted that there's a lot of FDT available in practice, but only these four methods will be discussed further in this video. As you can see from the slide, there are 4 methods, include sand replacement method, and then rubber balloon methods, core cutter methods, and finally the nuclear density gauge. A few videos from the YouTube were also attached to the slide for reference and better viewing of the field works taken on site. So let's start with the first one on sand replacement method. This slide shows the apparatus used for the sand cone, which consists of a sand pouring cylinder with pouring cone as its base. There is a shutter between the cylinder and the cone. Determination of field density using the sand replacement method involves 3 steps. The first step involves the calibration of a sand pouring cylinder. Second step refers to the measurement of the soil volume and soil density. And finally, the measurement of moisture content and dry density of soil. Okay, let's have a look on this step in details. Right, this is step 1. In this step, a few predetermined measurements need to be considered prior to field density measurement. The first one is to determine maximum dry density of soil that will be used on site using compaction tests in the laboratory. Then the sand cone equipment should be prepared, including the sand itself of known density. I repeat, the sand itself with known density. For good results, the sand used should be uniform, dry, and clean, which pass through 600 micron sieve size and retain over 300 micron sieve size with, again, known density. Finally, the mass of sand that fill up the cone need to be determined. As can be seen in this slide, based on the sketch, the sand is poured on a flat surface. And then the mass is calculated by taking the difference between mass of sand in the cylinder before and after pouring. So in this case, it's M1 minus M2. But why we have to measure this? Of course, the value will be considered later in the calculation of the field density. So stay with me to find out. After step 1 has been completed, now second step refers to the soil digging and sand replacement activities where both are conducted on site. So from the slide, you can see the photos of road surface after compaction. Now, let's assume that the soil is ready for the sand cone test. First, a hole with 4 to 6 inches is excavated manually after placing the metal tray on the ground. The soil should be kept in airtight container and later determined for moisture content. Then, the sand pouring cylinder is then placed over the hole, and the sand is allowed to fall into the hole until it is full. The weight of sand that fill up the hole is then noted as M4. Then, the volume of sand is calculated, which is similar to volume of soil that were excavated from the hole. And then finally, we can calculate the value of bulk density of soil. Next, step 3 involves determination of degree of compaction, which is the aim of the field density test. As mentioned in the previous slide, every layer has its own target of compaction level according to the specification. So next, continue with the determination of moisture content of the soil that recovered from the FDT, followed by the dry density of the soil. So detailed formula are shown in the slide. To determine the degree of compaction, or DOC, the ratio of fill density and the maximum dry density that we have determined earlier in laboratory is calculated. Here, I've attached a video for reference on the sand replacement method. The credit goes to the YouTube video with the link provided. The sharing is only for the purpose of education.
The following presentation demonstrates the use of the sand cone method to determine the moisture content of soil. We're going to need the following equipment: a scale, a proctor mold, plastic bottle, sand cone, base plate, trowel, and the evaporating dish. The first calculation we need to make is to determine the dry weight of the sand being used. For this, we need to first find the weight of the empty proctor mold. We get 3.788 kilograms. We'll refer to this weight as W1. Now we must fill the proctor mold level to the top with dry sand. Now we weigh the full proctor mold. We get 5.219 kilograms. We'll refer to this figure as W2. We need to know the volume of the proctor mold. In other words, how much sand can it hold? This volume is 0.00095 cubic meters, or V1. When we take W2, the combined weight, and subtract W1, the mold's weight, we then divide that value by V1, the volume. We get approximately 1,506.3 kilograms per cubic meter. That's the dry unit weight of the sand. The next calculation to make is to determine the weight of sand needed to fill the sand cone. The first thing to do is weigh the entire assembly of the sand cone and the bottle filled with dry sand. We get 7.076 kilograms. We'll refer to this weight as W3. Next, we make sure the cone's valve is shut. We invert the cone. Then, the valve is open so that a full cone of sand is released. The valve is to be closed again. Now we weigh the full assembly. We get 5.378 kilograms. We'll refer to this weight as W4. We can now determine the weight of sand required to fill the sand cone by subtracting W4 from W3. We get 1.698 kilograms, and we'll call that figure WC. Out in the field, we must first secure the base plate to a level area of ground. We now dig a hole about 10 to 15 centimeters deep. As you are digging the hole, put the retrieved soil into the plastic bag in order that the soil does not lose moisture. With the valve closed, turn the bottle and cone assembly upside down and place the cone in the center hole of the base plate and open the valve so that sand flows. After flow of sand stops, close the valve and pick the assembly up. The sand in the cone will be poured into the base plate. Back in the lab, we now weigh the complete assembly again. The weight is 3.529 kilograms. This is what we will call W5. If we take W3, the weight of a full sand cone assembly, and subtract W5 and WC, and divide it by the dry unit weight of the sand, we get the volume of the whole, which is approximately 0.00122 cubic meters. We'll call this figure V2. Our final calculations will require another series of weighing. We'll start with the evaporating dish. It weighs 0.462 kilograms. We'll call this W6. We then put all of the collected soil into the dish and weigh this. We get 2.723 kilograms. This is W7. Next, we put the evaporating dish and wet soil in the oven. After 24 hours, weigh it again. We get 2.621 kilograms. This is W8. Now we have all the data we need. We can calculate the moist unit weight of the soil by subtracting the dry weight, W8, from the wet weight, W7, and dividing that number by the volume of the whole, V2. We get 83.6 kilograms per cubic meter. To calculate the water content, subtract W8 from W7 again. This time divide that by W8 minus W6. We get 4.72%.